Very good evening to all the subscribers and viewers of Physics for Students. My name is Shounak, and today we have got a special guest from a distant part of where I live, and we would be talking about today with something which is very fascinating. Throughout the history of mankind and the entire endeavor of scientific world, we know that the origin of universe, how it all started, what are the implications, and most importantly, Big Bang, the very moment from which it all spread. This has been a matter which has been very curious, and we were all waiting to understand those things, and researchers mostly are currently going on in this field. And I take the pleasure today to welcome Dr. Professor Jessica Turner, an assistant professor of theoretical physics at the Institute of Particle Physics Phenomenology, Durham University in the United Kingdom. She is globally recognized as an expert in neutrino and early universe physics. She is also an author of the book Quantum Computing for the Quantum Curious, which I was going through, and it is an incredibly lucid understanding of something very complex. And she has got a Master's of Science from the University of Glasgow and internship from CERN. So I don't need to tell anything more about her. With a very warm virtual clap, let us welcome Professor Jessica Turner. Professor, a warm welcome.
Oh, thank you very much, Shounak. I'm very pleased to be here. Please call me Jessica.
Okay, fine. I will call you Jessica. Right. So very warm welcome. We have got, numerous people joining in. Numbers would be increasing slowly. We have got 7 right now, so there will be questions. So my first question, or rather I would say, if you can throw some light on this part, is that a basic overview of what neutrinos, the cycle, or the role that they play in early universe formation and evolution. If you can just tell us something more about that.
Okay, so first of all, I'll define what a neutrino is. So it is a spin-half fundamental particle. And by fundamental particle, I mean it cannot be broken down into smaller constituents. How does it interact? Well, it interacts via the weak nuclear force. So as you all know, there are 4 forces of nature: the strong nuclear force, electromagnetism, the weak nuclear force, and of course gravity. And neutrinos only interact with the weak force. The force carrier of the weak force are the W and the Z boson. And neutrinos can undergo 2 types of interactions. They can undergo charge current interactions, where their interactions are with the W boson, which is electrically charged, to create a charged lepton, or they can undergo neutral current interactions with the electrically neutral Z boson. So indeed, you can find neutrinos everywhere. Like every time an atom comes together, such as in nuclear fusion processes in the sun, or anytime an atom breaks apart, neutrinos are generated copiously. So for instance, the sun generates a lot of solar neutrinos, and we have about 100 trillion of these solar neutrinos streaming through us every second. So getting to your question about how neutrinos can affect the evolution of the universe. Well, first of all, one pervasive source of neutrinos are the so-called relic neutrinos, which were the neutrinos generated just approximately 1 second after the Big Bang. So very early on in the universe's evolution, the neutrinos were interacting with the hot plasma filling the universe via weak interactions. And these interactions before 1 second after the Big Bang were so fast, they exceeded the expansion rate of the universe. That means the neutrinos were in thermal contact with the thermal bath in the early universe. However, of course, as you know, the universe expands, the plasma contained within the universe cools, and those neutrinos could eventually lose contact with the plasma. And we say they would decouple. Now, they decouple when they're very fast and very hot, is what we would say, but naturally over time, their 3 momentum, or their velocity, reduces because the universe is expanding. Now, these neutrinos that pervade the universe today are called relic neutrinos, and there's approximately 330 of them for every cubic centimeter. Indeed, their presence would have affected the evolution of the early universe from the regard of large-scale structure formation. So when we look around our universe, we observe stars, planets that form galaxies, etc. We observe very large-scale structures. Indeed.
Okay.
So
Okay.
neutrinos. Sorry, Shounak.
No, please carry on. No problem.
So these neutrinos, which decoupled at very early times in the universe, they can actually affect the formation of this large-scale structure. And what we find is that from the observation of large-scale structures, we can actually constrain the sum of neutrino masses because essentially these free-streaming neutrinos could disrupt the large-scale structure formation if they're very, very heavy. Because essentially what happens is because they're moving very fast, they stop the clumping together of matter to occur efficiently. So through the observation of large-scale structure formation, we can actually infer something about neutrino masses and hence how they would affect the evolution of the structure we observe in the universe.
Okay. So my next question, Jessica, is that apart from neutrinos, were there any other particles which were very predominant during that time, or it was only the neutrinos?
So the neutrinos were never really a predominant part of the universe. So how we describe the universe's energy budget, it relates to the contents of the universe, right? So at present, if we look at the energy budget of the universe, neutrinos only comprise 1% of the universe's energy budget, whilst ordinary matter, so protons, neutrons, and electrons that make stars, galaxies, planets, and large-scale structures we observe, makes up about 5%. Dark matter's approximately 24%, and dark energy that drives the expansion of the universe makes up the remaining 74% or so of the universe's energy budget. So whilst neutrinos are important and they affect things like large-scale structure formation, cosmic microwave background observables, they were never a dominant component of the universe, but they are an important component nonetheless.
Right. So, Professor, one thing is that through the evolution of the entire cosmology, especially with Dr. Roger Penrose formulations, etc., what we right now can well understand that there was a point, one particular point where everything was very infinite and dense, and from there the entire expansion, etc., happens, and we are trying to go back to time and try to find out something which would eventually lead us to the formation. Now, I actually went through one of the lectures of Dr. Penrose, and he coined the term something called Aeons. Now, he was trying to say something possibly which was beyond the Big Bang. I mean to say previous even to that Big Bang. Any idea or anything would you like to explore on that part?
I have to say, I'm not familiar with this concept of aeons, and at least my research does not go back beyond, let's say, 10 to the minus 39 seconds after the Big Bang. So that's maybe a realm I'm not too comfortable to speculate on.
Right. Sure. So now the thing is that we often find that neutrinos are mentioned as ghost particles. What is the reason that we name by that?
Well, I think that analogy might come about because if indeed ghosts exist, they appear very seldom. And that analog carries over because neutrinos, even though they're very pervasive, as we just discussed, they appear to us very seldom because they are so difficult to detect. And that is related to the fact they only interact through weak interactions. Hence, they're very, very difficult to detect and very weakly interacting, like a ghost may be.
Okay, fine. So this might be a little bit, it might be an idiotic or a very foolish question to ask you. Now, we found that the unification of forces that are taking place, say, for example, quantum electrodynamics, then electroweak theory, etc. Now, because, as you told, the neutrinos interact with only the weak force, so the electroweak unification, the Sheldon-Abdus-Salam model, so does that carry any significance or any relation with the neutrinos?
Yeah, I mean, you can understand the interactions of neutrinos from the GWS, so the Glashow-Weinberg-Salam theory, and that's very, very important. Essentially, it tells you how you break from the SU2 left, which describes the weak interaction, and the U1Y, which is the hypercharge interaction, how you break this gauge interaction down to SU2 left cross U1 EM, or down to electromagnetism. So it's this theory that actually parameterizes the interactions of the charged particles and indeed the neutrinos, which are the neutral particles. So that describes all of those interactions that we've observed, and it's been very well tested, the theory.
Okay. So my next question to you is that, say, for example, the observation of neutrinos, I mean to say, does it really happen? How do we see, how do we understand those things?
So how do we know if we've detected a neutrino?
Yes. Yeah.
Okay, so how do neutrinos interact? As we were discussing, they can interact via charge current interactions, which means you have a neutrino coming in and it generates a charged lepton. So the charged leptons we are all familiar with predominantly are electrons, but there are also muons and taus. And muons and taus are, in all kind of meaningful sense, identical to electrons in terms of their quantum numbers, or how we would characterize them. Their only difference is they're more massive. So when for instance, an electron neutrino comes in, it'll generate an electron, and a muon neutrino generates a muon, and a tau neutrino generates a tau. So even though these interactions are very weak, if you do get a neutrino coming in, it can generate a charged lepton, and it's actually the detection of that charged lepton that tells us we've had a neutrino interacting with the medium.
Okay.
And we'll discuss these different medium, I believe, slightly later.
Right. So that means the one particle in some way generates a kind of a behavior which is something similar to the behavior of neutrinos, and then only we can detect it. Something like that.
Yes.
It goes by.
Yes. So you can't really directly detect the neutrino, but you can detect its interactions with a medium. So you can produce the charged leptons, or one might ask, what about the neutral current interactions? Well, you can have a neutrino coming in, and it can disturb, let's say, a nucleus, and that it can create some additional particles like photons or pions from the neutral current interaction with the nucleus. So it's really the subsequent particles that are created that tells us that a neutrino interaction occurred in the first place, as you stated.
Okay. So if I go a little bit technical, now what we can understand is that all those interaction of the particles are more or less described by the Feynman diagrams. I mean to say, this coming in, this is interacting, and this is giving to that. Now, this is a question which I mean to say, for example, we know that Feynman diagrams in particle physics has revolutionized the way. Now, for example, we do not have the Feynman diagrams. So my question to you, Professor, is that without the Feynman diagram, is it impossible, or there is no other alternatives to detect the annihilation and creation, or that is the only way out in which we can know?
Well, so the Feynman diagram, let me explain a little bit, maybe for some of the listeners who aren't familiar with this. So the Feynman diagram is a graphical way of representing particle interactions amongst each other. So you might have a neutrino coming in, an electron coming out, and it interacts with a nucleus. And the Feynman diagram allows us to essentially calculate a probability that this interaction would occur. So those are theoretical predictions. But of course, it's what we observe in the experiments that matters. So ultimately, what you observe in the experiments are a number of events. So you might observe a number of electron type events coming from electron neutrinos, a number of muon type events coming from muon neutrinos, etc. And you have to compare that with the theory inputs that tell you the probability these interactions happen. So and from the comparison of the theory prediction and the experimental observation, you can infer free parameters about the neutrino interactions that we don't understand or we haven't measured well yet. But I would say schematically, Feynman diagrams, they are the way we use, we calculate these interaction probabilities. However, that kind of pertains to the realm of perturbative calculations. Now, many of the experiments are based on detection with large nuclei, such as argon, in which case you need to model the properties of that nucleus using nuclear physics models, which do not use Feynman diagram type
Okay.
machinery. But you can actually factorize these two elements. So you can factorize the behavior of the nucleus versus the behavior of the actual particles, which are not composite like the nucleus, and still use the Feynman diagram approach for the particles.
So that means those which you're telling that has got a nucleus for the argon, etc., those won't behave according to the Feynman diagrams. So you can get an approximation. That's it.
Yeah, so what you can do is you can factorize the calculation. The nucleus is a much more complicated calculation than just the, let's say, the particles as opposed to the composite structure. Yeah.
Okay. So now what I was going through, I was, as you know, that I was constantly making new videos on quantum field theory, etc. So one thing, obviously, something which is relates to neutrino search, etc. Now, Professor, one thing is that, see, once we are going ahead with the researches day by day when things are increasing, starting with Newtonian mechanics, then with special relativity, then with general relativity, down, then with quantum mechanics, etc. So what is happening is that we are in the aim of marrying one with the other so that we can get a holistic picture. We also find that the mathematics is continuously increasing its complexities, because with Newton, we have to add special relativity, then with GR, then with quantum mechanics, then with Schrodinger equation, and so on. Now, this is often a question which my subscribers who are watching here also sometimes ask me. So I told that Professor Jessica would be there. Why don't you hear it directly from the horse's mouth? Is that this, addition of lot of theories makes the calculations a little bit more complex. I also find that there are a lot of infinities and renormalization needs to happen, etc. Now, my question, Professor, is that actually how do we deal, I mean to say, not on a technical way, but how do we deal with the mathematics if it is so large and complex? What is the generic understanding of how to reduce this equation so that it comes to a kind of a way in which we can understand? Or I would say the question in this way is that how this assimilation of different theories are constantly increasing the complexities, and how we, or you people, the researchers and scientists, how you're normalizing and making it happen. Is it all hardcore that you need to know the mathematics, or it is a kind of an intuition also which comes through study, that you slowly start to visualize certain things rather than pure analytics?
This is an excellent question and not an easy one to answer. Because I'm sure I could say one thing and many of my colleagues would then have different
I want your
opinions.
opinion. I think
I
the
think
viewers
it's
would
a
be
very,
happy
very
to
good
listen.
question. So I would say a good, if you want to be a theoretical physicist, a good mathematical grounding and training is necessary. But I think as a physicist, we aren't mathematicians. We can use mathematics as a tool to understand the universe. And in doing that, we're sorry, I was just a bit distracted by the question. And
I
in
will,
doing
I
that,
will highlight that. Yeah.
we learn to make controlled approximations, so we can have a very complex system and we can solve that complex system, but there are certain, and the complexity of the problem could increase ad infinitum, but with physical understanding, which effects are really important and which ones to neglect. Moreover, we often take limiting scenarios to check that the solutions of our equations make sense.
True.
And we call this a controlled approximation. So even though mathematical training and good training is essential, you need to understand what effects are worth including in your calculation. So formulating the question you want to ask before you solve the equations, and then also making controlled approximations accordingly, and having benchmarks that where your equations should give you the right solutions just to check that's all going well. But it's an excellent question and not an
Kind of
easy
a
one to
combination
answer.
of both intuitive mind and the high analytic brain. So through practice, you get a kind of an intuitive understanding when you see a complicated diagram that this particle is behaving, and then accordingly you try to solve things out.
Yeah, I mean, it's a very good point. Yeah, you build intuition once you've seen things enough. You think this interaction, okay, it should be smaller than this one because the coupling's smaller,
Right.
etc. I've seen this sort of equation before. I know what the kind of rudimentary solutions are, and I can kind of interpolate from there. So practice does build intuition, and you always make
Absolutely.
those cross checks that things limit in the right way.
Right.
Um,
I'll just take two questions and then we will proceed with our discussion. One is the Vikram Vishal is asking, neutrinos a Dirac particle or Majorana particle?
Right. So let me first define what a Dirac particle is versus a Majorana particle.
Sure.
So
Sure.
a Dirac particle is a particle which obeys the Dirac equation of motion. And that is essentially a fermion which has 4 degrees of freedom to parameterize it. Whilst a Majorana particle is also a fermion, but in addition, it obeys the Majorana condition, which relates the particle to the antiparticle in a kind of specific mathematical way. Now, what this condition does is it actually reduces from 4 degrees of freedom to parameterize the spinor field. It reduces, obviously, if you have a constraint on the spinor, it actually reduces the number of degrees of freedom in that spinor. And so it's a much more kind of economical way of constructing a spinor. So a particle that obeys the Majorana condition is a Majorana particle, and it only has 2 degrees of freedom to parameterize its spinor. In a very loose way, and it's very loose wording, one can identify the particle and the antiparticle. Whereas in the Dirac particle case, you need 4 degrees of freedom to parameterize the spinor, and particles and antiparticles are distinct. So for instance, an electron and a positron, they are the particle and the antiparticle, and they're distinct from each other. Whilst a neutrino, we don't know if it's actually distinct from the antineutrino. And this is an open question. So we don't know if neutrinos are Dirac or Majorana. And I think this is one of the most important open questions actually in neutrino physics today. And experimentalists are hoping to answer this question, and it will have many implications for theorists as well.
Very interesting question. So Vikram Vishal, you got your answer, and I thank Professor for answering this. Another from same Vikram Vishal is that neutrinos and antineutrinos are the same or different particles?
So that kind of relates to the question I was, the discussion we were just having there. So if neutrinos and antineutrinos could be treated equivalently, then the neutrino field, which is how we would describe it, obeys the Majorana condition, and that's not clear yet because we don't know if neutrinos are Majorana. I'm happy to talk about how we would discover if neutrinos were Majorana, if you want. But at present, we don't know.
Sure. Rocky is asking, do electrons actually travel backward in space-time diagram in Feynman diagram? Please do show some light on this misunderstanding.
They don't travel backwards in time. I think maybe you're thinking of a positron, which is the antiparticle of the electron, and you can interpret that as an electron traveling backwards in time. But if you were just to write down a fermion in a Feynman diagram, then it's not necessarily traveling backwards in time. But I understand your confusion, because that was Dirac's interpretation of what was coming out from like antiparticles, basically.
Sure. Take a few more questions with your permission, Professor. Vikas is asking, do quarks only have energy, not any matter?
So quarks actually do have, I'm not sure if I understand the question. Do you mean do they have mass?
So Vikas, if you can just elucidate a little bit on the comment section, I think that would be better. One question coming up, let Vikas answer. Why right-hand neutrinos don't exist on standard model?
Okay, so this is a very nice question. So one thing I should have said is that, well, I'm not going to go into detail about chirality, because it's hard to do that without bringing up a bit of mathematics. But in the neutrino, in the standard model, we have chiral interactions or left-handed interactions associated with the weak nuclear force. Now, neutrinos as we know them are left-handed. So we have left-handed neutrinos and right-handed antineutrinos within the Standard Model. Now, we've just never observed a right-handed neutrino or a left-handed antineutrino, so to speak, within our kind of testable framework. So that's why they're not part of the Standard Model. It's just purely by observation. We've not seen right-handed neutrinos yet. And if we did, that'd be very interesting, and then we'd have to modify the whole story of the Standard Model.
Right. He's telling that it will break the symmetry. So,
well, yeah, it would certainly allow lepton number to be broken. Yeah.
Another question from Vikram coming up is that why nature prefer left-handedness?
This is, I would ask myself that the whole time. I mean, why are there 3 generations of quarks and charged leptons and neutrinos? Why 3? Why not 4? Why not 5 or 2? It's not clear. I mean, you're referring to the actual structure of the symmetry of the Standard Model. Right. So one could just wonder, why is the Standard Model structure as it is? It may be due to, for instance, at a very high energy scale, in fact, the different symmetry sectors or the different gauge symmetry sectors of the Standard Model unify. And what we observe at our energy scale is the subsequent breaking of this larger symmetry. So into a left-handed sector. So it's not clear at the moment. We would have to understand what we call an ultraviolet or the high energy scale theory in order to answer that question.
Now, Interresistance is asking, can we describe with E8 lattice?
Well, I'm not very familiar with E8 lattice, but I could speculate you're thinking maybe that E8 would represent the symmetry group of a grand unified theory. That's what I would speculate. And yes, then that refers to what I was saying. If E8 was a good symmetry or a symmetry describing nature at ultra high energy scales, then the breaking of E8 down to our energy scales may manifest in this, would manifest in the Standard Model gauge structure if E8 was the symmetry or the grand unified symmetry.
Right.
So I know people have studied that, so it is a possibility, but it's not clear. One would have to test that theory.
Right. Another question coming up, Professor, if with your permission, what is the origin of the mass of neutrinos? Does it tell about 3 flavors?
So I think this might get to some of the interview questions, but should I answer it?
Yeah, actually, this was my next question. So it is good that Vikram Vishal have asked it. So that's wonderful. Yeah.
Okay, so let me talk a little bit just broadly about mass, if you don't mind, and then how Standard Model particles acquire their mass. Yeah. Okay, so first of all, I have a very unsatisfactory definition of mass. It's essentially anything massive cannot travel at the speed of light, and the more massive something is, the slower it will travel. That's the kind of rudimentary definition of mass. So it's not known how neutrinos acquired their mass. However, the other spin half particles of the Standard Model acquire their mass through the Higgs mechanism. So essentially, the theory you referred to, Shounak, the GWS theory, is the breaking of SU2 left cross U1 hypercharge down to SU2 left cross the electromagnetic symmetry. When this happens, essentially the Higgs field acquires a vacuum expectation value. And what that means is that throughout the universe, particles which are traveling and interact with the Higgs field essentially change chirality, and it's this chirality flipping that slows them down. So particles that interact more with the Higgs, like the top quark, it gets very slow, and hence its mass is very large because it has these rapid interactions with the Higgs field. So it's known that the Higgs gives mass to the quarks, the charged leptons, and the massive gauge bosons in the Standard Model. Now, neutrinos are very, very light compared with other particles. So we can make the analogy that the top quark is like the blue whale and the electron is like a rabbit. The neutrino mass in scale comparison would be of order a fruit fly. So out of the genus of particles, which are mammals, the neutrino is so light it cannot even be classified. It's not even a mammal. So it is extremely light.
That's wonderful.
It's extremely light. It's electrically neutral, so it's thought that it would possibly get its mass in an alternate way, and there are many proposed mechanisms for that. I mean, these proposed mechanisms can often tell you about the flavor structure, so how the different flavors of neutrinos are, mixing into each other. Does it necessarily tell you why there are 3 neutrino flavors rather than 4, so it doesn't necessarily tell you about that.
Okay. Vikas is asking, Professor, can quarks be divided into further particles?
As far as we know, not. They're fundamental particles. So
Right.
they are fundamental and cannot be broken down any further. And this has been tested very well.
That has been tested, right? Yeah. Professor, I am a little bit curious, if you don't mind, ask this question. What is your research is all about? What exactly you're researching and what are the possible outcomes? If you can let us know, I think that would be great.
Oh, thank you. That's very, very kind. So I am kind of a jack of all trades with neutrinos. So I'm interested in neutrino phenomenology and how we can use current and future experiments in order to better understand various theories. So theories that tell us how the neutrinos mix with each other, theories that tell us are there new states that interact with neutrinos, and theories that can explain why possibly neutrinos get, or how neutrinos get their mass. I'm also very interested in grand unified theories, which some of the viewers were asking about, and how we can test grand unified theories at the next generation of neutrino experiments, and also using gravitational wave signals. I'm very interested in how the matter-antimatter asymmetry was generated and its possible link with neutrino physics. And more recently, I've been working on primordial black holes and how they can have non-trivial interplay with early universe observables.
So primordial black holes in the sense that those black holes which are created during the time of Big Bang, or if I may be wrong?
Yeah, so the ones I've been studying recently were created during the rapid inflation initially in the early universe's evolution, and they're quite light. And those primordial, they're called primordial because they're not astrophysical. They're not the big black holes we've seen, in binary systems in spiraling and giving gravitational waves that have been observed. These are very light, and they've actually already evaporated before nuclei could form. But even though they've evaporated very long ago, they can still leave a mark in the universe. And I've been studying how this interplays with dark matter and neutrino physics.
Okay, so in case that we detect a primordial black hole, say for example, that means what you are telling is that mathematically or through some experimental evidence, we can find out that yes, there was a primordial black hole, possibly not a location or at least the existence. Is that so?
So the primordial black holes, black holes can span huge mass ranges. They can go from 0.1 grams all the way up to very, very heavy, almost maybe of a fraction of a solar mass. So I'm talking huge order of magnitudes in the mass. So the ones I've been interested in are very, very light. They're not around today. They would have already evaporated. And really the only way you can test them is through the gravitational wave signal they would have generated in their last moments. So when they so if you had a lot of primordial black holes in the early universe, they're essentially matter for all intents and purposes.
Absolutely. Yeah.
And what happens is they evaporate via Hawking radiation, and for most of their lifetime they're around about the same mass. But at the very end of their lifetime, they evaporate extremely quickly. And so you have a universe which was initially dominated by matter, i.e. these primordial black holes, and then boom, they all evaporate at the same time if they all have the same mass, and you have a universe filled with radiation. And what happens is you can actually cause the gravitational potential to resonantly oscillate or vibrate. And it's this that generates the gravitational radiation that in principle could be detected by future, gravitational wave experiments such as interferometers or atomic interferometers. So it would be this sort of like secondary effect of their evaporation you would be searching for to determine if they had been present at very early times in the universe's evolution.
Right. Wonderful. Okay, so just a quick recap. Those who are joining late, we are in conversation with Professor Jessica Turner, and we are talking about a lot of stuffs. We started with neutrinos and now going up to black holes. I'm super excited. Few questions, Professor. One is that is there any ideas to explain graviton into large scale, explain G? This is coming from Amit, somebody called Amit's students.
So gravitons are the force carriers of gravity, and currently we don't have satisfactory explanations of quantum gravity, and we've not been able to test quantum gravity. So I assume you're kind of referring to quantum gravity tests.
Quantum gravity, yeah, I think so. Graviton obviously would be that, right?
Yeah, so there are different theories of quantum gravity, but none of those are readily testable or have, yielded significant results. Of course, we've detected gravitational waves, which is gravitational radiation, but that's different from detecting a single graviton.
Right. And he has got a same question, just a little bit broad one. Can you explain about antimatter?
So antimatter is just what we call, okay, let me just take an analogy. We have an electron. The antimatter particle is the positron, and what happens is if the electron and the positron meet, they can annihilate into a photon or, for instance, a Z boson. So in this way, we can study the symmetries of the particle, and we know what the antiparticle is. So if the particle had charge -1 in terms of electromagnetism, the antiparticle would have charge +1. And when they encounter each other, they annihilate into the force carrier of that particular symmetry, namely electromagnetism. So that's why, all the fundamental spin-half particles we're aware of, apart from the neutrinos, have an electric charge and therefore have a well-defined antiparticle counterpart. Whereas neutrinos, they could have their antiparticle counterpart, but it's not exactly clear. And that relates to the question posed earlier regarding if neutrinos are Dirac or Majorana particles.
Right. Vikram Vishal is asking another question. Neutrino mass, is it relativistic or rest mass?
Okay, that's a very good question. So neutrinos, we know they're very light, as we discussed. They're the fruit flies, maybe not the best analogy, but they're the fruit flies of the particle mammal analogy.
Right.
Maybe we should make it a better analogy. But anyway, so most interactions, as we were discussing, that produce neutrinos, where atoms come together or break apart, they're in natural units. They're what we call mega electron volt scale energies. Well, we know neutrino masses are sub-electron volt scale, so more than 1 million times less than the energy. Therefore, most neutrinos that we observe, all neutrinos we've ever observed are very relativistic. So that means they're moving with high velocity. Now, there's only one source of neutrinos that could be non-relativistic, so not moving fast today, and that is the relic neutrinos we discussed at the start of the podcast, namely the ones that were created 1 second after the Big Bang. Because even though they were very relativistic 1 second after the Big Bang, they've had about 13 billion years to slow down. So they may be non-relativistic today.
Professor, one question. I hope you won't mind asking this. What was your inspiration to become a theoretical physicist, chase after neutrinos, Big Bang? Early childhood, maybe any professor, in particular event that flared your entire scientific journey or your life you have dedicated, and you have been doing a lot of researches, coming out books. I keep on watching you on the LinkedIn. So any inspirational event which would inspire all of us, and what was your inspiration, if you can let us know?
That's a very large question. But okay, maybe I'll start basic. I really always enjoyed mathematics and physics, and I think theoretical physics is a very good marriage of mathematics and physics, because you're using math to understand fundamental behavior. Moreover, particle physics really I find very captivating because you're studying nature at the smallest possible scales. In early universe physics, I find very fascinating because you're studying the universe at the earliest times. And this is kind of a marriage of two very different scales, right? Very, very, very tiny scales versus very huge scales and very long time scales. So the fact I could use math to study these sort of extremes of nature is always fascinating to me. I've had lots of excellent mentors, and I certainly wouldn't be where I am if I, didn't have excellent people around me encouraging me. And part of what you do is that, Shounak. So, I'm sure all the students around the world who watch this are very grateful to people like you for inspiring them. For me, like through undergraduate degree, there were various sources of encouragement for me. Dr. Morag Casey at Glasgow University was always very helpful. I did a summer internship. So summer internships are great ways to get experience with the particle physics experimental department in Glasgow University. And that was wonderful. And through that, I got the experience to do a CERN summer studentship, which I would encourage anybody who's interested to partake in, because that is a wonderful program. And there were excellent lecturers there, such as Geraldine Servant, Rohini Godpal, who's a very prolific theoretical physicist in India. And it was just really inspiring to be there. And then that only encouraged me more. And during my PhD, my supervisor was always asking deep questions, insightful questions, and very driven for science. That's Professor Sylvia Pascoli. And then there's so many more people, it's hard to name everybody that's been helpful, but I've been lucky to have excellent mentors.
Right. Any particular moment, I would say, as we call it, annus mirabilis in case of Einstein, any particular moment or any particular, I would say, inspirational event which actually, created a kind of a total paradigm shift, and things started to change and you started to move in? Any particular lecture, any particular professor's talk, or anything that flared and, changed the entire horizon of study or your scientific researches?
I really enjoyed relativistic quantum mechanics with Dr. Chris White, who was at Glasgow University at the time. I found that absolutely fascinating, and meeting the Dirac's equation, and it was quite inspirational and motivated me a lot. I also did a master's project with theoretical physicists at Glasgow University. So now Professor David Miller and now Professor Chris White on amplitude calculations. And I really, really enjoyed that. And I thought if I could do something like this the rest of my life, I'd be a happy person.
Professor, with the coming, in a few days, we will celebrate the Teachers' Day, which is coming up. Very fundamental question. We understand we undergo a lot of mathematical complexities, sleepless nights, doing mathematics, etc. But one thing is also true that, as you told, that with the study, the intuition, I wrote us kind of an excerpt in LinkedIn a few days back, when at 3 o'clock after my studies, I was just going to sleep. And suddenly the Riemannian geometry, various complex tensors, suddenly it came to my mind as if that I am floating in a maze and some figures are coming up. Instantly, the Riemannian geometry complex problem I could solve. And I wrote a few lines just out of my own heart in the LinkedIn. What exactly, what is the underpinning factor, because you have gone through so many professors, what is the underpinning factor that makes a remarkable teacher? What is that, only one or two factor that makes up a great teacher?
That is a really hard question to answer, and probably a very important one as well, to be fair. I mean, there have been very many inspirational and captivating lecturers I've kind of met throughout my academic career. I'm trying to think of one or two unifying attributes. I think engagement with the subject and engagement with the students, and a deep understanding that you wouldn't necessarily glean from a textbook.
Yeah,
And
I think
also a
that's
willingness to engage with the students.
willingness to engage with the student. I think that
Yeah.
is the most important factor. So all the people, 11, 12 people who are watching right now, Professor Jessica's message would be, what makes up a profound teacher is the engagement. So those who are watching this live or would be watching later the recording, I think that would be the message to all of us, that in order to become a teacher, you need to engage the students.
I mean, it sounds very trivial, but you can be very, very accomplished research-wise and be very insightful. But if you don't have the intention to engage and
Right.
convey,
Absolutely.
then
Absolutely.
that is not meaningful. Right?
Absolutely, you're very right, Professor. I always think is that in this way, a little bit, I would say, unorthodox kind of a thing, that it is not that always a great scholar would be a great teacher. No, I think an ordinary person who has gone through the trifles and problems throughout the life can be a better teacher, because you can actually understand the pains of a student when he or she is unable to understand. But if you are a scholar throughout the career, then possibly you assume that he knows everything. And if you assume that he knows everything, then you try to explain up to this level. And those
Yeah.
people who are falling under this level would be, yeah. Thank you, Professor. Just few more questions. One is that is asking, ma'am, all our theories are based on relativistic causality, and it is nearly impossible to observe such things. If these type of events is happening, can we anyhow get any hint from nature of us happening?
I'm not sure if I understand the question correctly, but I mean, we do know certain constants of nature which we can always refer to, such as the speed of light, Planck's constant, and they don't change. So maybe, for instance, you're thinking of superluminal neutrinos. There was a kind of preliminary press release from Opera that seemed to indicate they'd essentially measured neutrinos traveling faster than the speed of light. And of course, that wasn't the case, because the speed of light, they had mismeasured the distance the neutrinos were traveling, and the speed of light is kind of the universe's speed limit. So I think we have a good measurement of causality. We know, for instance, like we can
Right.
produce neutrinos at a beam, for instance, and we can then detect them later in time. And that is a causal connection we can have, and that is, linked to the speed of light and, special relativity.
Right. Vikram Vishal is asking, while antiparticles have opposite charges and some other quantum numbers, they still have positive mass. So why not anti-mass or negative mass?
Yeah, that's a good question. So, yeah, mass is essentially a positive quantity. So this is related to what we would call an onshell condition. If you've encountered that in your dynamic studies, it's essentially saying that the energy squared of a particle is equal to its 3 momentum squared plus its mass squared. And particles can't have negative mass, if they respect the on-shell condition. And the on-shell condition basically says you have a real particle, and it must obey this relation between energy, momentum, and mass.
Right. I think that's great. Now, my few last questions. We know that neutrinos actually come in three flavors, like the electron, muon, and tau. So, how do these different flavors of neutrinos actually interact with each other?
Okay, this is a really important question, like one of the key concepts of neutrino physics. So we've discussed what flavors of neutrinos are. It means you have a neutrino, if it's associated with a given flavor of charged lepton, it's that flavor. So electron neutrinos are associated with electrons, muon neutrinos associated with muons. And the question is essentially, how do these interact with each other, these different flavors? So neutrinos are very interesting, not just because they're the fruit flies of the particle physics mammal analogy. They also have this unique behavior that you can produce a neutrino of a given flavor. So for instance, an electron neutrino can be produced from the fusion process in the sun. And as it travels some distance, it can actually transform into a different flavor of neutrino. So there is a non-zero probability you can detect that neutrino as a muon neutrino. And this is known as neutrino oscillations, this phenomenon, and it's very key to the behavior of the neutrinos. Essentially, this flavor changing and this chameleon-like behavior they can have.
Professor, what is actually keeping us in a problem? What is the bottleneck of unifying the big one, that is general theory of relativity, with the very small quantum mechanics? Is it that the high energy that it produces, we are unable to produce it in the lab, or is it the mathematical complications, or what it is, as per your vision?
Right. So I'm not a quantum gravity researcher, but I can say broadly speaking, we understand gravity at large scales and its behavior semi-classically, but we don't have a single well understood or tested theory of quantum gravity. And at least the way I would understand this is that it's very hard to test quantum gravity theories because the natural coupling of gravity is essentially inversely proportional to the Planck mass. So these are extremely suppressed interactions. So gravity is attractive, but it's extremely weak. If it's
Right.
extremely weakly interacting, it's extremely difficult to test. So even if you do have a satisfactory quantum gravity theory, it's really remarkably hard to test it, precisely because the graviton has very weak couplings, because essentially G Newton, if you relate it to, for instance,
Right.
really small.
Absolutely. Asian College of Teachers is telling, good evening, ma'am. I think a teacher will be a successful teacher if he or she has a sensitive mind, that he or she can understand the student's mind. I think you agreed to that.
I totally agree. I think that's an excellent point, and someone who's
Excellent point.
empathetic and can understand from someone else's view or the student's view makes a better teacher. Absolutely.
Absolutely. Shankojit Singh Roy is asking, in delayed choice quantum eraser, there is no hidden variable and EPR paradox is proved wrong. But is there any hidden constant in quantum eraser?
Okay, I have to admit this is outside the realm of my expertise, and I'm actually I'm not sort of
Not an
equipped to
issue.
answer that
Yeah.
question. I apologize.
No problem, no problem. Ma'am, what would be your message to the young people who are watching today's live? I always tell, I made videos on two factors. One is that the passion that you have, really the passion, versus the practicality in terms of running your life, getting a job, earning money, and surviving your family. Now, obviously,
I like that surviving one's family. Yeah.
right, absolutely. So the thing is that as far as India and the subcontinent is concerned, it is true that we get great researchers, scientists, young students who have got a brilliant mind, but maybe due to some reason they are unable to pursue their particular research due to certain incumbents. What would be your advice, and what is the future of neutrino and early research if persons from here they take up, and how they would go ahead? What would be a kind of a career advice from your side to those young people who are now 17 in number, those who are watching today? How would you guide them? What would be, let me know in twofold. What is that? One is that I would want a very honest answer from you, that I always tell my subscribers and students, stand in front of the mirror, assess you that really do you understand mathematics. It is not scoring high, it is not getting great marks, but is your brain really wired to that one? And what would be the steps? How would you tell them what are the specializations, etc., after getting a grad or undergrad? How would you tell them? If you, that would be really wonderful. A person like you, I think you would be the right person to show a kind of a guideline on this type of research.
So, Shounak, I think you make an excellent point. I think assessing whether you have some aptitude in for mathematics, coding, numerics, analytic thinking is necessary. If you've taken the necessary steps and you see, okay, I perform reasonably well, if I make a good enough effort in these courses, then I think you should pursue, if you want to, further education on physics and mathematics. So I should say India has very many excellent institutions. So I visited University of Delhi back in 2017,
Oh,
and
you
also
came to
visited.
Delhi?
Yes,
Oh, that's wonderful.
for physics research, and there are
I should have met
excellent.
during that time.
Are you in Delhi, Shounak, or
No,
where are you?
I often go on and visiting places.
Well, yeah, it was an excellent visit, and I was very inspired to work with the scientists there. And I also visited Institute of Physics Bhubaneswar in Odisha, And there's an excellent neutrino physicist there, Professor Manimala Mitra. And so there's lots of amazing institutes and incredible researchers and immense human resources in India. So I don't think there's lack of places to study, excellent institutions to study within India. And I've seen a lot of the open access education on YouTube from Indian institutions, and the level of education is high. So if you could attend a good I'm not sure of the ranking, but I know there's plenty just from these resources, a good university for physics and mathematics, that's good. Try and apply yourself where possible, and reach out to people if you're interested in their physics. I did look at some scholarships that were available to me. This is not an exhaustive number of scholarships, but there are Commonwealth Master's scholarships for people seeking master's degrees. So if you've attained your undergraduate university education in India and you wish to study in the UK, for instance, to get some different perspective, or if you have a researcher you'd like to work with, that may be one option. There's also the Commonwealth Shared Scholarships and Commonwealth PhD scholarships, as well as Chevening scholarships. And I'm happy to share the Durham University's scholarship website with you, which lists several different scholarships. There are more postgraduate, so master's and PhD scholarships available than undergraduate scholarships. But I would say, like, if you can, if it's not accessible for you to study abroad, there's very many excellent institutions within India. And if you get a good, if you push yourself to do well at an undergraduate degree in physics or mathematics, if you want to study in the UK, there are these scholarships available. And of course, if you are income limited, it is very difficult. But I think, which refers to the question that was asked earlier, if you are working and studying, you should probably let your professors know.
Right, absolutely.
Because they will want you to succeed.
Absolutely, that's true. That's true. Their cooperation, I think, would be something different to you, because if you're working and studying. Thanks, Professor. That is a wonderful guidance. Two quick questions. I know we are going beyond time. This is something different from Mark, and he's asking that how art can influence discoveries in science. Einstein put himself in the shoes of God, maybe to view world from first-person perspective. Any thoughts, ma'am, on significance of art?
Oh, this is a wonderful question. I think, in a way, well, my husband tells me that doing theoretical physics is a little bit like being an artist.
So your husband is also into science and mathematics?
Yeah, he's a trained physicist, but now works in robotics. So he tells me, you're pretty much an artist with what you're doing. There's no
That's wonderful.
Immediate impact on society, such as maybe he's designing automated warehouses, which has more of a immediate impact. But there is the sort of cultural value. So I think great art can inspire people. It can, and that is the main sort of crosstalk, I would say. I really enjoy visiting art galleries, and I have some favorite art pieces around me, and they make me feel.
I can see right at the back, I think you've got some paintings.
Yeah, this is a painting by a friend of mine, actually, Linnea, which I enjoy. And then I think also science can inspire art.
Inspire art, absolutely, absolutely. Last question, because we are exceeding the time, and I have requested Professor to come after a lot of adjustment of time. So let us say I have an idea. This is a question from Vikram Vishal. Electron neutrinos converted into tau neutrino, its speed changes. Is there any experimental design to test this hypothesis?
So there is, these would be non-standard interactions, and these can be constrained by oscillation experiments.
Okay.
But it's, I should say, one, yeah.
Shankajit is asking, are the flavor of neutrinos incomplete and are the leptons still not completed? What is ma'am's opinion that are the leptons incomplete in metastable state? Can we extract another type of neutrinos?
So I interpret incomplete as, are there other generations? So we have the
Generate.
electron
Right.
neutrino, the muon neutrino, and the tau neutrino. The question is there some other flavor of neutrino? So there may exist a sterile neutrino, which would be a fourth type of neutrino. It doesn't interact with electrons, muons, or taus at all, but it actually mixes with these flavors of neutrinos. So in essence, it could be a fourth generation, for instance. So that possibility is not excluded entirely. So a lot of the parameter space has been excluded by various experiments, but the entire possibility or entire parameter space has not been excluded. Fourth, if there's a fourth lepton, that's been heavily constrained by Large Hadron Collider searches. But the possibility there's a fourth neutrino has not been excluded.
Right. So, Professor, I think we might have a lot of questions, and it can go out throughout the evening, but we have to pause. I think your camera is freezed. I cannot see you anyway. So, any last message, Professor, you would like to tell to all our viewers who are watching right now?
I would just say stay engaged, stay inspired, and Shounak, thank you so much for the kind invitation. It's been a real pleasure to discuss with you, and I'm very inspired with all this effort you're making to, broadcast physics and mathematics.
I am always trying to tell. I told my subscribers that I would continue inviting professors, because doing videos is one aspect. I know that I can do a little bit of good work, but bringing you on board and asking, so you can see there are many questions that are constantly flowing on. And I know that if I can keep for 1 more hour, it would be more. But anyway, we have to. So she's telling, thanks a lot, Jessica, and she is given a sign of love. So all those appreciations coming for you.
I'll give a sign of love back. Yeah, thank you to all the listeners and for these amazing questions. I'm sure. They're very creative and very insightful.
Yeah, and from one teacher to another teacher, wishing you all the best on the Teachers' Day. And thank you very much. This is the usual Indian way to thank you.
Thank you very much.
Thank you very much for coming. And we won't let you go, because when your time permits, we can, take up a time, and we will like to bring you on board, because it is a absolutely amazing session. I never thought there will be so many questions. It would be constantly question and answer. And you see, I have not even answered 50% of my question. Is still in the notepad, but it is absolutely great, because I have to answer all the questions, and it is the subscribers who matter. And I think they are pretty happy after listening to you. So thank you, Professor. A good night from India, and wishing you a very happy Teachers' Day, and heartfelt thanks, gratitude from Physics for Students and from me, Shounak. Thank you, Professor.
Thank you. It's been an absolute pleasure, and happy Teachers' Day to you when it comes.
Thank you.
Thanks for the questions, everybody.
Yeah. So Shankarjit is saying thanks. So thank you. Bye. Bye. Bye.
Goodbye.
Bye, Professor. Goodbye. Bye. Take care.